Hello everyone, this is the second video of Beckmann rearrangement where we will see different types of examples. Now it will be better if you watch the previous video, that is the first one where I have discussed the mechanism in detail so that you can connect to this video in a better way. First we will see how to write quickly the Beckmann rearrangement product when a particular starting material is given. So here you can see the ketoaxime, right? And there is a dotted line between the R and R prime. So this may be connected, this may not be connected. If it is open structure, you will get amide. If it is cyclic, you will get lactam. And the cyclic ring size, that will also increase. So see, in the starting material, we have a ketoaxime, and when you will write the product, you have to add this extra NH between this R and R prime. That is, between R and R prime, there will be now CONH. Now, depending on which R group will migrate, accordingly, the N will be connected to that R group. And why the ring size will increase? Because if you look at the starting material, here we have a single carbon atom between R and R prime. But in the product, we have NH group and carbon. So that is why one extra atom is added. Ring size will increase. Now, what is the intermediate through which it is happening? It is the imidinol. So first of all, the group which is anti to the OH, that is migrating. So as you can see, the R group is migrating. And in this particular position, that is the original position of the carbon R group, that position there is a OH. So this is the imidinol. Imine, C double bond N, and OH, imidinol. In presence of acidic catalyst or rearrange, it will be formed. And after tautomerization, so this OH bond will be broken and NH will be attached to nitrogen atom. So we are getting finally the product. And what type of acidic catalyst and reagent we use, that I have already discussed in the last video. Here you can see it once more. So it may be that is some protic acid, some Lewis acid, so different varieties are there. Now one by one we will see the examples. The first example here, this NOH, you have to find the anti group. So this is the anti CC bond. Now suppose the anti group, it is not possible to understand from the structure given. Here you can understand it, but suppose this NOH, it is directly written like this, then it is not possible for us to understand which group is anti to OH. In that case, you can simply go by the electronic factor. That is, from the point of view of electronic factor, the group that should be migrating, you should choose that group. So here that problem is not present. So that is why this CC bond will be broken and it will be now connected, that is this carbon will now be connected to the nitrogen in presence of TSCl pyridine, that is the acidic reagent or catalyst we are using here. So this is the tosyl group TS, in case you do not have any idea about this group. And finally we are getting the product. So see, 5-member ring, previously this is 5-member, now it is 6-membered. Why? Because now nitrogen is also part of the ring, and this is the connection point. I mean to say, this CN bond is the newly formed bond and this CC bond is broken. This is example 1. Next example is, now this is interesting because we have a chiral center here, and as you can understand, this is one R group, this is another R group. Which R group is anti to OH? It is this, that R group containing this chiral center. Now in presence of Ac2O, we are getting the product where the chiral center is intact. So whenever you will have to write the Beckmann product and there is a chiral center, that is the migrating group is having some chiral center, it is always better you do not disturb this chiral part. So that is why, see, when I have drawn the molecule, that is the product molecule, this part I have kept same. Only this, instead of this CN part, now we have this NC part. Okay, so it is better to write in that way. If you want to, suppose if it is R configuration, it will remain R. If it is S, it will remain S. So this is the second example. Example number 3. Now we do not have the ketoaxime directly. Some carbonyl compound is given. So you have to do the first step. You have to do the oxime formation step. Then we have the Beckmann rearrangement condition. So mostly you will see problem will be given to you in this fashion only. Okay. So in presence of NH2OH, first you will prepare the oxime. Now the question arises that two types of oxime you can get, right? So see, in presence of NH2OH, you are getting this one as the major. Why I am saying this is major? Because here we have at that is with respect to C double bond N, at 2 position we have a R group. So we will expect that when the OH is opposite side of this R group, that will be major from, if we consider the steric factor, right? Now if this is the major, in presence of TSCl, this OH that will be converted to OTS. So obviously from the major oxime we will get this NOTS, which is our starting material for the Beckmann, that will be major. And if this is major, now this CC with this R group, so this part now it will be broken because it is opposite side of the leaving group, and now we have a new connection here. So that is why now the ring size will increase. Previously it was 6-member ring, now it will be 5-member ring because the nitrogen is also part of this. And remember, this group is now, which is basically the R group, I have written here as R to simplify the structure, and R group is now here. That is the full structure as you can see in the product side. Now if you are interested to know the nitrogen intermediate, I have directly written, but here if you are interested to know this, see, this is the structure of the nitrogen intermediate, where this OTS group is removed and this carbon nitrogen newly formed bond is present. Fine. Example number 4. Here also first you have to prepare the oxime in presence of NH2H, and next reagent we have acetic acid. Now unlike the previous example, here we have some protic acid CH3COOH, right? So that is why something different will happen. As you have seen in the previous case, we are simply choosing the major oxime and then we are moving from that. But here something different will happen, and that we'll see here. First of all, you have to prepare the oxime, and looking at the structure you can understand which one will be major. Obviously this large tertiary butyl group, it will try to remain opposite side of the OH group because of the steric factor, right? So that is why this is, the left hand side is minor, this one is major. But remember, here we have protic acid, and as I have already discussed this in the last video, so that is why you should watch the last video so that you can understand what, because I will not go into the details again, that will be wastage of time. That is not the purpose of this video, right? So what happens if you have some protic acid medium? Now the product that you are getting, you have to write the product on the basis of electronic factor. Now between pH and this tertiary butyl group, you have to give preference to pH. That is from electronic factor, migrating tendency, you have to give preference to it. And that is why as pH is migrating, pH will be connected to NH. So here this factor we have to keep in mind, that rate of isomerization or interconversion, as we have some protic acid environment, that is greater than the migration or rearrangement. And that is why you cannot say that whether we should move from the major or minor. There is no such thing. You simply have to rely on the electronic factor. So this particular factor is already discussed in the last video. Please watch that part. So here migration we are deciding based on the electronic factor. We are not considering any minor or major. Okay, because if you consider the major one, just we have done it for the last example, then tertiary butyl group should be connected to it. But that we have not done, right? Because we have chosen that one which is based on electronic factor. Okay, so this is the final product structure. Next example 5. So two structure, as you can see, left hand side and right hand side. Why I have written two? Because try to understand difference. Here we have carbon bromine bond. Here we have hydrogen, right? Now what is the difference happening? Rest of the part of both the structures are same, right? Now no reagent is there, but suppose any Beckmann reagents conditions are present. So what will happen? Here this group is anti to the OTS group. So this CC bond will be broken and this will be migrating here. So this is the expected that you are seeing here. This is expected, right? So that is why this 6-member ring, now it will be 7-member ring. And this is the this CC bond is broken, not the other CC bond. So this is our expected product. But when Br is present, now something different will happen. In presence of Br, it can attack N. It is ideally situated in such a way that it can easily do it, right? And OTS will be removed. And when OTS is removed, see, as if this structure is already blocked here. You cannot break this CC or CN, this time migration. No, that is not possible here. So that is why the another thing that is happening here, right? So what will happen if you break this CC bond? Now positive charge will be generated at this position. So let me do the numbering. Suppose this is 1 carbon, this is 2 carbon, right? So now 2 carbon is attached to N. So this is our 1 carbon, that is the original carbon. 1-2 bond is broken, and between 1 and 2 now you have the nitrogen. And as this is that is different mechanism if you compare with the previous right hand side molecule. So we are getting the opposite product. See here NH is connected to this ring junction, but here CO is connected to the ring junction. So that is why it is not always you have to check the molecule. If you simply follow the rule of Beckmann, that is the general rule, that is the group which is always anti to the living group, you are simply migrating that. Don't do that always. Just check in the molecule, the environment of the molecule, where the reaction is actually happening, if any other possibilities are there, because mostly something different will be given. It is not the straightforward question will be given where directly you can apply the rule. Mostly that will not happen, right? So you just have to check whether any other possibilities are there or not. Next example, here we can see some stereospecificity. So see, we are starting the reaction with a mixture of geometric isomers. What is the difference? So here we have this part is same, right? But only difference is whether the OH is anti to pH or whether the OH is anti to this OH ortho position OH and pH. That is a different pH. So if it is pH, suppose this is something aryl group, it is not direct benzene ring, right? So two different colors I have used so that you can understand what is happening here. So if you look at the product side, from the color you have to understand that from A, that is the violet one, you are getting product which is this one. Suppose this is A prime, and from B you are getting B. Also from the color it is clear. Now why it is so? It is simple, because pH is anti to OH in case of the violet starting geometric isomers, right? Now if it is so, this pH group will be migrating. If this pH group is migrating, now you can see this N-pH bond, right? And finally water will attack at this carbon and you will get C double bond O. So this is simply straightforward. There is no something different is happening. But something different will happen if you consider the green molecule. Why? Here this AR group, aryl group, that will be migrating because this is anti to OH. Now if it is migrating, now this OH group, it is suitably situated in such a way that it can easily attack this carbon. And when it is attacking this carbon, you are getting a 5-member heterocyclic ring. Now this type of thing you cannot do with the violet one, because if you want to do the same type of thing, it will be a 4-member ring which is not stable. But this one is ideally situated, 5-member ring formation, fine. So that is why we are getting this type of 5-member ring. Okay. So the same thing again I will say that look at the environment of the molecule if something different can be formed. So suppose in options this structure, that is this intermediate, and then water is attacking, you are getting C double bond O here. That option, that product will also be given. But there is further reaction possible where you are getting ring structure. So that will be given to another option. So you have to check whether the other possibility, so that you can choose the correct option, right? Example 7. So this is the starting material oxime. You have to start from here. Now if you move in the left hand side where H2SO4 PPA is given, reagent reaction condition, and another side we have TSCl and PDD. Now look at the right hand side first, because here we are getting the expected product. Why I am saying expected product? Because see, here one side of the oxime you have methyl, another side you have some chiral center, right? Now this side obviously it will here you cannot understand which group is anti or something like that, so you can simply consider the electronic factor, and from electronic factor this should be migrating, that is fine. And also this chiral center, that should remain intact. That means if this is above the plane, this bond CC bond, that should be same. So here we have this expected product, and as this part is migrating, so that will be connected to nitrogen, and that we are getting also in the right hand side. So this is the cis isomer. Why it is this? Because cis decalin system, this group and this group both are above same side. So this is the expected product, right? But what is happening in presence of the other side, that is the left hand side? Here we are getting the trans isomer, trans decalin system, and this is the violation of the rule of retention of configuration, right? So this example is given from Carrey Sandberg, and the page number I am giving you 954. If you want to go into the details of the mechanism, the reference is also given there. So in presence of this another reaction condition, something different is happening here. Fragmentation, that is, it is not direct intramolecular mechanism. In the last video also I have discussed it in detail that there is alternative mechanism of Beckmann where direct intramolecular group migration is not happening. First there is a CC bond cleavage and carbocation is there. Now there can be recombination. So this part, as you can see, CH3CN, it is removed, right? You are getting carbocation. This carbocation is stable. So that is why it can happen. Now the nitrogen, it will be connecting with this carbon. So this is the recombination. Don't confuse it with Beckmann fragmentation. That is completely different thing. Here final product is just like Beckmann product, but it is going through not intramolecular fashion, but there is a CC bond cleavage, complete cleavage, and then the nitrogen is attacking. Fine, and you are getting this type of trans arrangement. So this mechanism is occurring through fragmentation plus recombination. It is not the normal Beckmann mechanism. It is the alternative mechanism that is detailed discussed in the last video. Okay, and this example is taken from Carrey Sandberg, page number I have given. Next example, here also you can see two different types of products we have, two different types of starting material we have taken together, and they are completely different molecules. Both are oxime, that is fine, and these groups are different. Here we have methyl and tertiary butyl, here we have ethyl and benzyl group. In presence of H2SO4, here it is written total 4 amide products. So the question can be constructed in such a way, suppose this starting material mixture and in presence of H2, so it is given to you and it is asked that how many products will be generated, and there will be different options. So your answer should be 4. Now why it is so? Suppose if you consider the expected product, that is, suppose the green molecule is given individually and the violet is given individually, then what you will do? Obviously this group you will be migrating. So there will be C double bond O, then NCMe3, and that is the expected product. Similarly from the violet also, you will be getting, this group will be migrating because it is anti-2OH. So N will be connected to the benzyl group. So these are the expected product. You will get both of them, right? You will also get the other possibilities, and these are the cross products. So here also this CC bond is completely broken, and this can happen because if it is completely broken, the positive charge carbocation, that is very stable, and here also the positive charge benzyl, that is also very stable. So these type of possibilities are there. Now if you are considering these cross products, then 2 more products are possible. So the fragment from the violet that can be attached to the green, and the fragment from the green that can be attached to the violet. Okay, so that is why cross products. So if you consider all of them, we are getting total 4 amide products. Okay, so that's all for this video where we have seen diverse examples, and in the next video there will be discussion, that is the abnormal Beckmann mechanism. Okay, so thank you for your time.